Hello everyone, so I'm Quentin Kral, astronomer at the Paris Observatory, and today I want to tell you about the gas that is now discovered around main sequence stars and that may affect planetary atmospheres, both for rocky and giant planets. Well, as you understood now, I'm not going to talk about the young protoplanetary disk phase in this talk, but rather focus on what happens after 10 million years once the planets have formed, but that there's still some gas around that can last for some hundreds of millions of years. I want to show you that actually planetary formation is not over after the protoplanetary disk stage, and many interesting interactions can still happen that can affect planet atmospheres. As a teaser, I can say that the remaining gas in these planetary systems, which is mostly made of volatile species, will accrete onto the already formed planets and substantially change their atmospheres. Let's see the questions you may have in mind at the moment. Tell me if I'm right. So you may wonder whether the accreted gas can change an existing atmosphere in a noticeable way, and whether this late volatile delivery helped to form the first building blocks of life on a rocky planet. Well, let's see that now. So for those of you that aren't really familiar with circumstellar disks, let me tell you about planet formation in 30 seconds. So you know at first when you have a star forming, still surrounded by a large cloud of gas, which is going to rapidly turn into an accretion disk, which we see here. That's the protoplanetary disk phase. This disk is full of gas, full of dust. Protoplanets are forming. And then very rapidly, we end up in the debris disk phase, which is the phase our solar system is in, where the star is on the main sequence. There's a series of planets. There are planetesimal belts. The planetesimals in these belts are going to collide with each other and create dust or debris, hence why we call them debris disks. And what's new here in the debris disk phase is that now gas is discovered in this old phase as well. So you may think that all the planetary formation is happening at the protoplanetary disk stage, but I'm going to show you otherwise in this talk, and that there's still a lot happening at the debris disk stage as well. So just to recap quickly, the protoplanetary disk phase is the young phase where protoplanets are forming. But what I'm going to be telling you about in this talk is the debris disk phase, really, which is the remnant of planetary formation. It can last for a few giga years. What's new is that now in this phase as well, we detect gas, which I'm going to call late gas in this talk. And this late gas can be captured onto planets and affect the composition of planet atmospheres. So just for you to kind of see what circumstellar disks look like, they're complicated beasts with asymmetries, with gaps that may be related to hidden planets. And so let's talk about how to deliver volatiles to a planet. So what you may be familiar with is this one, the delivery of volatiles by exocomets, which is, you know, on Earth, for instance, a comet falls, impact onto Earth, and it delivers some water or some volatiles. But this is not what I'm going to be telling you about today. What I'm going to be telling you about is a new mechanism, which is called late gas disk accretion. So let's start by telling you what late gas is. So far we detected 20 late gas disks. And what we know is that if we take a volume limited sample of bright debris disks, then what we find is that almost all of them have gas. So the conclusion is that late gas disks are the rule rather than the exception in debris disks. So, you know, I just want to show you what this gas looks like on the sky when we observe it, for instance, around Beta Pictoris, a famous debris disk with ALMA. So you see, we can see CO at quite high resolution here with an asymmetry. We can see neutral carbon. In the past with Herschel, we could target neutral oxygen and ionized carbon. In the UV or optical, we can even target heavier metals such as neutral iron, and so on and so forth. And this is giving us a good overview of the gas evolution and composition. And what we can get out of it is that we can get access to the exocomet composition in these extrasolar systems. So you see the gas is released from the planetesimals. And so as we have access to the gas, we can go back to the composition of the volatiles on the planetesimals from which it was released. And we do that for a few systems. And we see that actually the COI mass fraction on the planetesimals seems to be consistent with the range of composition of the solar system comets, except for a few systems, which I'm showing on the right here, where upper limits are already showing less CO than in solar system comets. This is when we push ALMA deeper, we can see that. So let's get to the heart of this talk now, which is telling you about this paper about the formation of secondary atmospheres on terrestrial planets by late disk accretion. So in this paper, we're basically saying that late gas is released in the planetesimal belt. It's going to viscously evolve inwards and encounter the planets, and it's going to fall on the planet to be accreted onto the planet. And in this paper, we quantify how much gas is actually accreted by planets it encounters. And what we find is that actually the accretion is quite efficient, and it can be dominant in setting up the final composition of terrestrial planet atmospheres. Just for you to know, this late gas is made of CO, and there may be also some CN and water released, and it's going to feed the planets for hundreds of millions of years. So that could be something of interest for people working on the development of the first bricks of life, because there's really a continuous influx of volatile onto the planet, which could help really. So you may wonder how efficient that is and whether it can change our thinking on how planetary atmospheres evolve. And I'm going to be telling you about that now. So, you know, I told you that we quantify how much gas is accreted onto a planet. This is what I'm going to show you on the plot here. So for different gas crossing rates, which you see at the top of the plot, there's going to be different evolution. So for the lowest gas crossing rate, 10 to the minus 8 Earth masses per megayear, you can see that it's going to be an Earth-like atmosphere that's going to be created after 100 millions of years of evolution. But if you take the highest gas crossing rate, you can even create sub-Neptune-like planets. So it seems that this mechanism is very efficient on rocky planets around main sequence stars. I'm showing the same plot here on the right-hand side. I just want to give you a feel of the m dot value on the left-hand side for different planetesimal belts. So you can see that if you take a Kuiper belt, low mass belt, you end up with an m dot value on the order of 10 to the minus 7 or 10 to the minus 8 Earth masses per megayear, which can create Earth-like atmospheres. But if you take a very massive disk of 100 Earth masses, you can see that you end up with m dot values of between 10 to the minus 1 and 10 to the minus 2 Earth masses per megayear. And you can make drastic changes to your atmosphere and create a sub-Neptune-like planet. So in terms of pressure, you can see on this plot on the left-hand side, you reach like 1 bar pressure very easily, 10 to the 2 bar Venus-like pressures, or even 10 to the 5 bars, thanks to this mechanism. And you can see in terms of bulk density as well, the drastic changes that can be made to the atmosphere. And it seems that this mechanism works for close-in planets as well as for more distant planets. It works for super-Earth planet and for less massive planets as well. So it seems to be kind of a new general way of forming planet atmospheres. And now let's talk about giant planets. There's going to be a long-term effect and a short-term effect. The long-term effect is that as we're accreting a lot of high C2O ratio and high metallicity material, the metallicity and the C2O ratio are going to increase in these giant planets while they're ongoing accretion. And you can see that on this plot, that late gas disks are going to affect the primordial C2O ratio on sub-Neptunes, Neptunes, or Jupiters. So what we need now is more measurements, for instance, with the JWST or aerial, that would help test our scenario further. The short-term effect is that, you know, there's going to be like an accumulation of gas on the outer layer of, say, a Jupiter, and it's going to take time for the gas to drift inwards into this Jupiter. And so it's going to pile up a little bit on the outer layer of the planet. And so it's going to create some extra CO absorption that could be actually seen in the M-bounds when there is ongoing accretion. And that's something that could be detected with the JWST for the coldest giant planets or even for brown dwarfs. And that would be a clear confirmation of ongoing accretion in the targeted systems. So a corollary of all of that is that it gives a new planet detection methods. So you understood that if you have a planet that's an efficient accretor, then nothing is going to come inwards in the system. And so it's going to naturally create some cavities. And if you detect the cavities, then you can detect the planet locations. And this is something you could do with ALMA, pushing it at really high resolution, for instance, on the C1 line, and you could detect terrestrial planets at several AUs from their host stars, which is something that can't be done with other methods, for instance. So I'm leaving you with the mini conclusion here, and I thank you for reaching the end of the talk, and I'm happy to answer any question you may have.